Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The celestial sphere, for millennia, had been a source of wonder and a framework for understanding time and space. By the late 16th century, the precision with which humanity charted this celestial realm was revealing its limitations. The prevailing cosmological models, particularly the sophisticated toolmake system, while capable of predicting planetary positions with a reasonable degree of accuracy for everyday purposes, struggled with the finer points of celestial mechanics, accumulating discrepancies, subtle yet persistent, hinted at a deeper complexity that the existing observational data and theoretical constructs could not fully accommodate. Astronomy, at its core, is an empirical science built upon the data gleaned from watching the heavens. For centuries, this observation had been a solitary pursuit, relying on the keenness of the human eye and the ingenuity of relatively simple instruments, astrolabes, quadrants, and armillary spheres, while elegant in their design and indispensable for their time, were constrained by their size and the inherent variability of naked eye perception. Measuring the precise position of a star or planet involved aligning a sighting device, often a civil ruler or pointer, with a celestial object against a graduated arc. This process, repeated countless times by numerous observers, introduced a cascade of potential errors. Atmospheric conditions, the observer's own visual acuity, the precision of the instrument's markings, and even the subtle wobble of the observer's hand could all contribute to variations in recorded data. Furthermore, the sheer volume of data required to discern the intricate dance of the cosmos was staggering. To truly understand the subtle deviations from established orbits, astronomers needed a continuous, systematic record. This meant observing the same celestial bodies repeatedly, night after night, year after year, under varying conditions, and meticulously documenting every observation. Such a commitment demanded resources, dedication, and a structured approach that had, until then, been largely absent from astronomical practice. The intellectual landscape lacked empirical foundation. Questions arose, anomalies were noticed, yet the tools and methodologies to answer them with required rigor were still developing. Into this realm of burgeoning questions and observational constraints emerged Tycho Brahe, a figure whose life and work irrevocably altered the course of astronomy. Born into Danish nobility in 1546, Brahe possessed an intellect that far outstripped the conventional pursuits of his station. His early fascination with the heavens was ignited by a spectacular solar eclipse in 1960, an event whose predictable occurrence, yet profound visual impact, captivated his young mind. This astronomical marvel, observed from his youth, spurred a lifelong dedication to understanding the celestial order with a precision that transcended mere philosophical contemplation. Brahe's early astronomical studies were undertaken with the instruments of his era, but his inherent dissatisfaction with their limitations quickly became apparent. He recognized that the path to unraveling the universe's secrets lay in a systematic accumulation of highly accurate observational data. This conviction led him to conceive of a project of unprecedented scale and ambition the creation of a dedicated observatory, a veritable temple to the stars, equipped with instruments of his own design, far exceeding anything previously attempted. The realization of this vision took shape on the island of Hven, a strategically chosen location between Denmark and Sweden. Here, under the patronage of King Frederick II of Denmark, Brahe erected Uraniborg, a name derived from the Greek for heavenly castle. Uraniborg was a statement of intent, a monument to empirical inquiry. Its construction represented a profound investment in the infrastructure of astronomical observation. The facilities were designed with meticulous attention to detail, incorporating specialized rooms for observation, calculation, and the housing of his ever-expanding collection of instruments. The very design of Uraniborg reflected Brahe's commitment to minimizing observational error. Observatories were positioned to provide clear, unobstructed views of the sky, and the instruments themselves were engineered for stability and accuracy. Brahe recognized that the caliber of astronomical knowledge depended directly upon the caliber of observational data. He endeavored to eliminate as many sources of uncertainty as possible, encompassing the stability of his instruments, supporting structures, and the accuracy of the graduated scales employed for measurement. This dedication to cultivating a superior observational environment represented a significant advancement. Before Brahe, astronomical work frequently occurred in less specialized settings, utilizing instruments that were either portable or adapted from other uses. Brahe's methodology involved constructing the observatory around the instruments, and the instruments around the requirements of precise measurement. He understood that the celestial sphere constituted a vast and intricate subject, and that comprehending it necessitated a sustained, systematic, and instrumentally supported undertaking. His resolve was to establish a new standard for astronomical practice, one where rigorous data collection served as the fundamental basis of all investigation. This constituted the initial phase, the preparation of the site, and the establishment of the foundation for more accurate comprehension of the cosmos, a dedication to empirical truth that would shape his enduring influence, and pave the way for subsequent astronomical breakthroughs. The immense celestial sphere, a panorama of predictable, orderly movement for ages, posed significant challenges to those aiming to meticulously chart its complexities. In the latter part of the 16th century, the very process of ascertaining the exact position of a star or planet was an undertaking laden with intrinsic obstacles. The prevailing astronomical models, though refined in their design, relied on observational data that frequently mirrored the limitations of measurement more than the actual condition of the cosmos. A principal impediment was the inherent inexactitude in graduating the scales of instruments. In the absence of uniform, finely divided arcs and circles, astronomers had to interpolate between markings, introducing a degree of subjectivity and error that accumulated with each observation. Consequently, the angular distances and positions, vital for understanding celestial mechanics, remained approximations, their accuracy constrained by the tools utilized. Further complicating this was the pervasive effect of atmospheric refraction. As light from celestial bodies traveled through Earth's atmosphere, it bent, causing objects to appear higher in the sky than their actual locations. This effect varied with the altitude of the celestial object and atmospheric conditions. A star near the horizon would be significantly displaced from its actual location, and this displacement was variable. Early attempts to correct the refraction were rudimentary, often based on theoretical models that failed to capture the dynamic nature of the atmosphere. Consequently, observations made at lower celestial altitudes were systematically skewed, leading to a distorted view of the heavens. The prevailing understanding of stellar parallax, for instance, was hampered by this atmospheric distortion, making it exceedingly difficult to detect the subtle shifts in stellar positions that would indicate Earth's motion. Furthermore, the instruments themselves, while often ingenious, lacked the robustness and standardization necessary for high-fidelity astronomical work. Many were constructed with materials that could warp or shift, and their mounting systems were frequently inadequate, allowing for subtle movements that corrupted observational data. The very process of taking a measurement often introduced new sources of error. Whether it was the alignment of sighting devices, the parallax of the observer's eye when reading a scale, or the stability of the instrument during the observation, each step was a potential gateway for inaccuracy. The prevailing astronomical practice, therefore, was one where the pursuit of absolute certainty in celestial positions remained an elusive goal, a testament to the limitations of the observational toolkit. Tycho Brahe, driven by an unyielding desire for empirical accuracy, recognized these fundamental limitations. He understood that the grand questions of cosmology, the true arrangement of the heavens, the nature of celestial motion, and the Earth's place within it could only be answered through data of unprecedented quality. His solution involved conceiving and constructing entirely new instruments designed from the ground up to achieve unparalleled precision. This involved a profound commitment to engineering and a meticulous attention to detail that redefined the very practice of astronomical observation. At the heart of Brahe's innovation lay his creation of massive, fixed instruments. Unlike the portable quadrants and astrolabes of his predecessors, Brahe's instruments were monumental structures anchored securely to his observatory at Uraniborg. This immobility was crucial, eliminating errors arising from the instrument's movement or shifting during observation. His great quadrant, for example, was an immense arc spanning nearly 24 feet, its metal limb precisely graduated. The sheer scale of this instrument allowed for finer divisions of the arc than previously possible. The problem of graduating these scales was addressed with painstaking care. Brahe employed skilled craftsmen to etch the divisions, ensuring uniformity and clarity. He further refined the process by using sighting devices such as alidades with pinions that allowed for the precise alignment with celestial bodies. These pinions, often equipped with small holes, enabled observers to pinpoint the exact moment a star or planet passed a specific degree mark, minimizing the subjective element in reading the angle. The issue of atmospheric refraction was tackled with a similar dedication to empirical investigation. While Brahe undertook systematic observations to understand its effects, he did not possess the sophisticated mathematical models of refraction we have today. He observed stars as they rose and set, meticulously recording their apparent positions. By comparing observations of the same celestial object at different altitudes, and by observing the same altitude at different times of night and year, he began to build a practical understanding of how the atmosphere altered celestial positions. He developed empirical correction tables based on these observations, which represented a significant leap forward in accounting for this pervasive source of error, although they were perhaps not perfectly accurate by modern standards. His commitment was to measure the error and then to subtract it, bringing the observed data closer to the true celestial positions. Brahe's ingenuity extended to the design of his instruments to minimize the observer's own errors. He utilized elaborate sighting mechanisms that reduced the parallax error inherent in reading scales. His instruments frequently incorporated multiple sighting vanes, enabling the observer to align celestial objects with exceptional care. The observer's position also received stabilization, and the instruments were engineered for reading from a fixed vantage point, further diminishing variability. He recognized that even the most precise instrument could become inaccurate due to a poorly conceived observation method. Consequently, his observatory exemplified a comprehensive approach to measurement, integrating the instrument, the method, and the observer into a system engineered for peak accuracy. His armillary spheres, extensive metal frameworks depicting the celestial sphere, served as prime examples. These were functional measuring devices, or exceeding mere decorative models. The rings representing the celestial equator, the ecliptic, and the meridians were constructed with precision and graduated meticulously. Through observing the passage of celestial bodies across these rings, Brahe could ascertain their coordinates with unprecedented accuracy. His instruments were built for longevity, fashioned from resilient materials such as brass and iron, and subjected to careful upkeep. This devotion to the physical integrity of his tools held significance equal to the precision of their calibration. He appreciated that the heavens were dynamic, requiring the tools used for their measurement to be equally sturdy and dependable. His commitment to establishing a superior observational environment was groundbreaking. Before Brahe, astronomical endeavors often occurred in less specialized environments, utilizing instruments that were portable or adapted from other uses. Brahe's strategy involved constructing the observatory around the instruments, and the instruments around the requirements of precise measurement. He understood that the celestial sphere presented a vast and intricate subject, and comprehending it necessitated a persistent, systematic, and instrumentally supported endeavor. His commitment was to establish a new paradigm for astronomical practice, one where rigorous data collection was a cornerstone of all inquiry. This was a foundational step, the clearing of the ground and a laying of the bedrock for a more accurate understanding of the cosmos, a commitment to empirical truth that would define his legacy and set the stage for the astronomical revolutions that followed. The celestial sphere, as understood for millennia, presented a picture of sublime, unchanging order. The Aristotelian cosmos, a framework deeply embedded in philosophical and scientific thought, posited a fundamental division of the terrestrial realm characterized by change and decay. The celestial realm, a domain of perfect, immutable spheres carrying the planets and stars in eternal circular motion. This elegant edifice, refined and extended by Claudius Ptolemy, provided a comprehensive, albeit complex, geocentric map of the heavens. However, the very foundations of this worldview were destined to be challenged by phenomena that defied its inherent principles. The heavens, it turned out, were dynamic. In the year 1372, a brilliant new star blazed into existence in the constellation Cassiopeia, outshining all other stars and even visible during daylight hours. This was no fleeting atmospheric illusion. It persisted for many months, gradually fading but undeniably present. For Tycho Brahe, this was a profound moment, a direct confrontation with established dogma. The prevailing Aristotelian view held that celestial bodies were perfect and unchanging. New stars could appear, and existing ones could alter their brilliance or position in a way that suggested transformation. The Aristotelian explanation for such transient celestial events, when they were acknowledged, attributed them to atmospheric disturbances or ephemeral phenomena occurring within the sublunar sphere below the moon. Tycho Brahe, however, approached this startling apparition with his characteristic commitment to empirical evidence. He meticulously observed the new star, charting its position relative to known stars and noting its apparent brightness over time. His observations, conducted with the superior instruments he had commissioned and housed in his new observatory, Uraniborg, allowed him to determine that this new star possessed a fixed position among the stars. It did not exhibit the parallax, the apparent shift in position due to the observer's changing viewpoint, that would be expected of an object within Earth's atmosphere. Objects close to us, like clouds or meteors, exhibit noticeable parallax as we move. The presence of no such parallax for the Muddy's Infinity 72 star indicated that it resided far beyond the terrestrial sphere, among the fixed stars themselves. This was a radical assertion, directly contradicting the Aristotelian principle of celestial immutability. The heavens, it seemed, were capable of change after all, and this change occurred at a distance that rendered the ancient classifications problematic. The year 1577 brought another celestial spectacle that further tested the limits of the existing cosmological model, a magnificent comet. This comet, visible for months, traversed the sky with a brilliance that captivated Europe. Again, the Aristotelian framework struggled to accommodate such an event. Comets were typically categorized as atmospheric phenomena, fiery exhalations or vapors igniting in the upper reaches of the Earth's atmosphere. Yet, the mighty 577 comet displayed characteristics that defy this explanation. Brahe undertook a systematic program of observation, comparing the comet's position with that of the moon and other celestial bodies. He employed an ingenious method, observing the comet from different locations on Earth. By comparing the apparent direction of the comet from two geographically separated points, he could, through triangulation, estimate its distance. His calculations revealed that the comet had no discernible parallax. It was simply too distant for any apparent shift in its position to be detected when viewed from widely separated terrestrial vantage points. This meant the comet was a celestial object moving through the region of the planets or beyond the moon. This finding was particularly damning for the Aristotelian system, which placed the moon's orbit as the boundary between the mutable sublunary realm and the immutable celestial spheres. If a comet could traverse the realm of the planets, planets. The very structure of the cosmos, as understood for centuries, was fundamentally flawed. The heavens were composed of perfect, crystalline spheres. They were a dynamic space where objects, including comets, could appear and move in ways that were radically different from the ancient descriptions. Brahe's meticulous recording of these events, his rigorous application of observational techniques, and his insistence on empirical data provided powerful evidence against the long-held Aristotelian cosmology. The new star demonstrated that celestial bodies could appear and change, and the great comet of 1577 proved that such phenomena were confined to Earth's atmosphere, but were indeed celestial travelers. These were merely observations. They were empirical refutations of deeply ingrained philosophical assumptions about the nature of the universe. Brahe's work thus presented a critical intellectual challenge how to construct a coherent understanding of the cosmos that could accommodate these new, undeniable facts about celestial dynamism and the true distances of cometary bodies. The stage was set for a new cosmological vision, one that would arise directly from the meticulous data collected by Tycho Brahe. His work illuminated the limitations of ancient models, revealing a universe far more complex and active than previously imagined, and demanding a reevaluation of humanity's place within it. The celestial sphere, a seemingly immutable dome of fixed stars and predictable planetary circuits, presented a profound intellectual puzzle. For centuries, the Aristotelian geocentric model, with Earth as a moving center, had provided a framework for understanding the cosmos. As observational precision advanced, cracks began to appear in this venerable edifice. The very data that Tycho Brahe meticulously gathered, the star that blazed anew, the comet that traversed the heavens, began to whisper of a universe far more dynamic, far more expansive, and far more complex than the ancient philosophers had conceived. A primary challenge confronting astronomers of Brahe's era was the inability of the geocentric model to adequately account for fundamental astronomical phenomena. The most glaring of these was the absence of observable stellar parallax. If Earth were indeed in motion, orbiting the sun, as Copernicus had boldly proposed, and the apparent position of nearby stars should shift against the background of more distant stars throughout the year, this shift, or parallax, would be a direct consequence of our changing vantage point in space. However, no such shift was reliably detected. The stars appeared fixed, their relative positions unwavering. The prevailing view held that if Earth moved, we would perceive a constant, observable shift in the celestial panorama. The failure to detect the shift was taken as evidence of Earth's placid stillness. Furthermore, the intricate dance of the planets, their retrograde motions, and varying brightness strained the explanatory power of the geocentric system. Epicycles and deference offered a way to describe these observed movements, presenting an elaborate mechanism designed to fit the data, rather than a fundamental description of celestial mechanics. The inherent elegance and simplicity sought by scientific inquiry seemed to elude this complex layering of circles upon circles. The observed paths of the planets were predictable in their general form, yet the underlying cause of their apparent deviations from simple circular motion around Earth remained the subject of intricate geometrical manipulation rather than a clear physical explanation. It was against this backdrop of observational contradiction and theoretical complication that Brahe formulated his own cosmological proposal. He acknowledged the compelling evidence for a dynamic universe, a universe where comets were celestial bodies traversing vast distances, and where the heavens themselves contained objects that could appear and disappear. He recognized the difficulty in reconciling these observations with the established geocentric framework. The apparent stillness of the stars, the lack of detectable parallax, presented a significant obstacle to accepting a moving Earth. Brahe's solution was a masterful synthesis of observation and tradition, a compromise that sought to preserve the perceived stability of Earth while accommodating the newly revealed dynamism of the heavens. He proposed a geoheliocentric or Tychonic system. In this model, the Earth remained at the center of the universe, stationary. The Moon and the Sun orbited the Earth. All the other planets, Mercury, Venus, Mars, Jupiter, and Saturn, were depicted as orbiting the Sun, which in turn revolved around the Earth. This arrangement offered a unique resolution to the observational quandaries of his time. The Tychonic system elegantly addressed the problem of stellar parallax. Because the Earth was stationary, the absence of observed stellar shift was perfectly explained. The stars remained fixed in their celestial sphere, their apparent positions unchanging from a stationary terrestrial viewpoint. This aspect of his model resonated deeply with those who found the lack of parallax to be an insurmountable argument against the Copernican system. Brahe's model offered a way to embrace the observed celestial phenomena without requiring a moving Earth, thereby satisfying a critical observational constraint that had long troubled proponents of heliocentrism. Simultaneously, the Tychonic system retained the Copernican explanation to the planetary motions. The retrograde motion of planets, for example, was naturally accounted for by the fact that the planets were orbiting the Sun at different speeds. As Earth, in its orbit around the Sun, overtook slower-moving planets like Mars, or was overtaken by faster-moving inner planets, their apparent motion in the sky would seem to reverse, creating the characteristic loop of retrograde movement. This aspect of Brahe's model allowed him to incorporate the predictive power of the Copernican heliocentric arrangement for the inner solar system, while anchoring the entire structure to an unmoving Earth. The Tychonic system represented a significant intellectual achievement, a bold attempt to reconcile conflicting evidence and deeply ingrained philosophical beliefs. It was a model born from a profound respect for empirical data, a testament to Brahe's commitment to letting observation guide theory. He was content to address the lack of parallax. He sought a framework that could explain it. He was also willing to embrace the predictive success of the Copernican scheme for the planets. His geoheliocentric model provided a middle ground, a sophisticated compromise that allowed astronomers to continue observing and refining their understanding of the cosmos without immediately discarding the intuitive notion of a stationary Earth. This proposed arrangement of celestial bodies offered a coherent picture of the universe, one that acknowledged the apparent stillness of our planet while embracing the observed complexities of planetary orbits and the reality of celestial motion demonstrated by comets and nova. It was a system that sought to bridge the gap between the perceived and the empirically known, a testament to Brahe's unique position at the cusp of astronomical revolution. The observational legacy of Tycho Brahe extends far beyond the ingenious compromises of his geoheliocentric system. His enduring contribution lies in the sheer, unprecedented volume and meticulous precision of the astronomical data he amassed over a lifetime. The scientific landscape of the late 16th century was characterized by a desperate need for reliable, long-term observations, particularly concerning the planets. Existing celestial catalogs, often centuries old, were riddled with inaccuracies, making the testing and refinement of nascent cosmological models a frustratingly imprecise endeavor. Theories, however elegant, foundered when confronted with observations that were either too sparse or too flawed to provide meaningful validation. Brahe recognized this fundamental deficit. His ambition was to propose a new model of the cosmos and to provide the empirical bedrock upon which such models could be rigorously scrutinized and, if necessary, corrected. The instruments he designed and employed, such as his monumental quadrant and armillary sphere, were marvels of engineering for their time, built with an unwavering commitment to minimizing observational error. He understood that the perceived motions of celestial bodies were subtle, and that capturing these nuances required instruments of unparalleled skill and craftsmanship, coupled with an observer's unwavering dedication. His efforts to quantify the heavens involved painstaking routines, night after night, regardless of weather or personal comfort. Brahe and his assistants meticulously recorded the positions of stars and planets. These were systematic measurements, cross-referenced and checked for consistency. The sheer scale of this undertaking is difficult to overstate. Imagine the dedication required to track a planet's arc across the night sky, day after day, year after year, translating those observations into precise numerical values, all while contending with the limitations of pre-telescopic instrumentation. This commitment to empirical rigor transformed astronomical observation from a somewhat speculative art into a disciplined, quantitative science. The culmination of this monumental effort was a treasure trove of data, a comprehensive celestial atlas, and a detailed record of planetary movements that stood as the most accurate and extensive compilation of its era. This collection of observations, comprising thousands of star positions and hundreds of planetary measurements, represented a paradigm shift in astronomical practice. It offered a tangible, reliable foundation for theoretical exploration, providing a basis for the astronomical knowledge of previous generations. This vast repository of empirical knowledge found its most profound application in the hands of Johannes Kepler. Upon Brahe's death, Kepler, who had joined Brahe's Uraniborg Observatory shortly before the latter's demise, inherited this unparalleled data set. Kepler, a brilliant mathematician and astronomer in his own right, was tasked with the analysis of this data, a task that would consume years of his life and ultimately revolutionize our understanding of planetary motion. The problem Kepler faced was immense to reconcile the observed planetary paths with the prevailing theoretical frameworks. He began with the Copernican model, which placed the sun at the center of the solar system, but found that even its predictions fell short when tested against Brahe's precise measurements, particularly for the planet Mars, the elliptical orbits, the varying speeds of planets along their paths, the very geometry of their celestial journeys. These were secrets hidden within the dense columns of Brahe's observational logs. Kepler's genius lay in his ability to tease these secrets out. He meticulously analyzed Brahe's data, performing calculations that were both mathematically demanding and conceptually groundbreaking. He allowed the data to speak for itself, revealing its own underlying order. This was a direct transfer of Brahe's legacy, the raw, unadulterated truth of the cosmos, captured by an observer's unwavering gaze and meticulously recorded through diligent effort. Brahe's data provided the critical empirical evidence that allowed Kepler to formulate his three laws of planetary motion. These laws, derived directly from the observations collected at Uraniborg, described planetary orbits as ellipses, established that planets sweep out equal areas in equal times, and related the orbital period of a planet to the size of its orbit. These represented a fundamental redefinition of how celestial bodies move through space. They offered a predictive power and an explanatory depth that had been unattainable with the less precise data of earlier epochs. The impact of Brahe's data, therefore, was transformative. It moved the field of astronomy from an era of qualitative description and approximate calculation to one of quantitative precision and rigorous empirical validation. The observational foundation laid by Brahe provided the essential fuel for Kepler's theoretical engine, demonstrating how the painstaking accumulation of accurate data could unlock profound insights into the workings of the universe. His observations served as the indispensable bridge between the geocentric and heliocentric worldviews, providing the empirical weight needed to move beyond the intuitive, Earth-centered perspective and embrace a more accurate, sun-centered reality, albeit one with orbits far more complex than Copernicus had initially envisioned. The legacy of Brahe's numbers was the birth of modern celestial mechanics. The astronomical observations of the late 16th century, while increasingly sophisticated, presented formidable challenges in their practical execution and subsequent utilization. The sheer volume of data generated by meticulous charting of celestial positions demanded innovative solutions for organization and accessibility. Astronomers of the era grappled with the inherent limitations of recording vast quantities of measurements, ensuring their accuracy, and disseminating these findings to a wider scientific community. The challenge was a grand logistical undertaking, akin to building a comprehensive library of the heavens, where each entry had to be painstakingly verified and systematically arranged. Tycho Brahe's approach to this intricate problem was characterized by an unparalleled dedication to methodology and organization. He recognized that the value of astronomical data resided in its accuracy, its systematic management, and its clear presentation. His observatories, particularly Uraniborg on the island of Hven, were designed as sophisticated scientific institutions. These were environments built for precision, equipped with instruments of unprecedented scale and design, and staffed with assistants to manage the laborious process of observation and calculation. Brahe's instruments, such as the large Miro quadrant and the armillary sphere, were engineered to minimize observational error. The sheer size of these instruments allowed for finite divisions of the celestial sphere to be marked, and the use of sighting vanes and plumb lines, all meticulously calibrated, contributed to an accuracy that surpassed anything previously achieved. The problem of parallax, for instance, a persistent source of error in earlier measurements, was addressed through Brahe's careful construction and utilization of instruments that allowed for more stable and precise readings. He understood that even minute inaccuracies, when accumulated over countless observations, could lead to significant discrepancies in astronomical models. Brahe implemented rigorous protocols for data recording. His observational logs were detailed, capturing the celestial body observed and its position, the date, time, atmospheric conditions, and the specific instrument used. This level of detail was crucial for ensuring the reproducibility of his observations and for allowing future astronomers to assess the reliability of his data. The problem of data loss or corruption was mitigated by his systematic approach to cataloging and his insistence on multiple checks and cross-references. He was essentially pioneering early methods of scientific data management, creating a robust system for storing and retrieving information. The dissemination of this accumulated knowledge was another critical aspect of Brahe's vision. While many of his extensive catalogs and observations were published posthumously, his active engagement with other scholars and his correspondence played a vital role in sharing his findings and methodologies. He understood that scientific progress was a collaborative endeavor, and that raw data, however accurate, required interpretation and integration within broader theoretical frameworks. His willingness to engage with the scientific community, even when his own cosmological model differed from prevailing views, fostered a spirit of open inquiry. Brahe's efforts to create a comprehensive and accessible astronomical database were foundational. The sheer scale of his collected observations, spanning decades and encompassing thousands of stars and planetary positions, represented a significant leap forward in the empirical study of the cosmos. This systematic accumulation of high-quality data provided an unprecedented empirical foundation for astronomical theory. The problem of insufficient or unreliable data, which had long hampered astronomical progress, was confronted directly by Brahe's tireless commitment to accurate measurement and meticulous record-keeping. His work laid the groundwork for the quantitative analysis of celestial motion, transforming observational astronomy into a discipline grounded in empirical evidence. The legacy of his organized data collection was the creation of a reliable empirical bedrock upon which future astronomical discoveries would be built. A paradigm shift in how celestial phenomena were studied and understood. Tycho Brahe's monumental undertaking redefined observational astronomy. His meticulously crafted instruments, such as the Great Quadrant and the armillary sphere, were extensions of his unwavering dedication to empirical truth. These instruments, are exceeding the precision of their predecessors, allowed for the measurement of angular positions with unprecedented accuracy, a feat achieved through ingenious design and the implementation of rigorous observational protocols. The problems of his era were deeply rooted in the imprecision of existing astronomical data, a limitation that perpetuated a geocentric worldview and hindered the development of more accurate celestial models. Brahe's solution was a systematic, decade-long commitment to observation, conducted with instruments of his own design and a methodology that emphasized consistency and verification. He sought to create a celestial atlas of unparalleled fidelity, an empirical atlas that would serve as the definitive reference for astronomers for generations. The sheer volume and quality of data Brahe amassed were revolutionary. His observations of the comet of 1577, for instance, provided crucial evidence against the prevailing Aristotelian notion of immutable celestial spheres. Brahe demonstrated that the comet traversed planetary orbits without disturbing them, thereby challenging the very structure of the cosmos as understood for centuries. This was a pivotal moment, shifting the focus from philosophical deduction to empirical evidence in understanding celestial mechanics. Brahe addressed the problem of reconciling observed phenomena with established cosmological models through a direct confrontation with the evidence. His careful tracking of the comet's parallax revealed it to be closer than the moon, a finding that directly contradicted the Aristotelian hierarchy placing all celestial bodies beyond the lunar sphere. This single observation, born from meticulous measurement, began to unravel the ancient, Earth-centered universe, whereas extensive observations of Mars, particularly its retrograde motion, further solidified his empirical approach and proved instrumental. The problem of accurately describing planetary orbits, a persistent challenge within the full-make system, found a more amenable, albeit transitional, solution in Brahe's own geo-heliocentric model, the Tychonic system. Brahe's model proposed that planets, except for Earth, orbited the Sun, which in turn orbited a stationary Earth. This ingenious compromise allowed him to incorporate the observational elegance of Copernicus's system while adhering to a more philosophically comfortable geocentric foundation, a testament to his pragmatic approach to scientific reconciliation. Brahe tackled the problem of explaining the complex, often erratic, movements of planets with a model that, while geocentric in its outermost shell, acknowledged the Sun as the central point for the inner solar system's orbital dynamics. His solution offered a framework that could accommodate the growing discrepancies in tool-make predictions without demanding a complete upheaval of the established cosmological order. The enduring legacy of Tycho Brahe lies fundamentally in the unparalleled dataset he meticulously compiled, alongside his instrumental innovations and his cosmological propositions. This vast collection of stellar and planetary positions, gathered over a lifetime with unwavering accuracy, provided the essential empirical foundation upon which future astronomical revolutions would be built. Brahe's solution to the problem of a lack of reliable, long-term observational data was the creation of an empirical database so comprehensive and precise that it would continue to yield profound insights long after his death. His observations of the star catalog, detailing the positions of over 1,000 stars with unprecedented accuracy, offered a stable celestial reference frame. This stability was crucial for identifying subtle changes in stellar positions and for tracking the apparent motion of the Sun and planets with greater precision than ever before. The problem of understanding the true nature of celestial motion was confronted by Brahe through a commitment to systematic, long-term data collection. He understood that the transient nature of individual observations could be overcome by amassing a continuous record. His dedication to this principle meant observing the same celestial bodies repeatedly, under varying conditions, and meticulously recording every detail. This approach transformed astronomy from a more speculative endeavor into a discipline grounded in empirical verification and quantitative analysis. The modern relevance of Brahe's work is profoundly evident in the foundational principle of rigorous, systematic data collection that underpins all scientific inquiry. His relentless pursuit of accuracy, his innovative instrument design, and his creation of an unparalleled astronomical database represent a paradigm shift in how the universe is studied. He demonstrated that progress in understanding the cosmos is inextricably linked to the quality and quantity of empirical evidence gathered. The data Brahe generated, particularly his precise measurements of planetary positions, would become the raw material for Johannes Kepler. Kepler, privy to Brahe's vast observational orbit after the latter's death, utilized this rich empirical resource to formulate his laws of planetary motion. The problem of describing planetary orbits with mathematical precision, a challenge that had eluded astronomers for centuries, found its solution through Kepler's analysis of Brahe's data. Kepler's first law describing elliptical orbits and his second law detailing the varying speeds of planets were direct consequences of the accuracy and comprehensiveness of Brahe's observations. Without Brahe's life's work, his instruments, his methodologies, and his meticulously recorded data, Kepler's groundbreaking discoveries would have been impossible. The legacy is clear. Brahe provided the empirical bedrock upon which the edifice of modern celestial mechanics was constructed. His commitment to observable fact and the precise measurement of the heavens irrevocably altered the course of scientific history, ushering in an era where empirical evidence reigned supreme in the quest to understand our place in the cosmos. His life's work stands as a testament to the power of meticulous observation and the enduring value of data in unraveling the universe's grand designs.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.